Okay, we're ready for the next problem. Problem number 2 on this worksheet, this practice problems, we're not going to do it. We are not going to do that problem. Don't worry about that problem. That was something, it was a demonstration I was going to do for you, and it's based upon that demonstration. I don't have the materials to do the demonstration here at my abode, so I can't do that one. So you can cross it out. Don't worry about it. I will not ask you about question number 2, problem number 2 on next week's academic adventure. But problem number 3, yes, we are now prepared to solve problem number 3. It says a bug is super glued to a tire. So essentially, by gluing the bug to the tire, the bug is part of the tire. So, and this tire is spinning around. So the bug is spinning around on the tire that's glued to. I know it's mean. I'm sorry. So we have glued the bug, part of the tire, spinning around. It says, what is the angular distance? Angular distance, angular. Oh, that means I'm going to have to use radians. We're going to have to use radians to solve this problem, because angular means radians. Distance the bug travels in 3 minutes oh, it says in radians right there anyway, so yes, that's radians. On the rim of the tire that starts spinning from rest. So the tire starts spinning from rest. So you got this tire, maybe it's like a bicycle tire, you know, it's got all these spokes on it. And we glued the bug there, bug. And we are going to, is starting from rest. So the bug's been glued on, and he's, I don't know if it's a he or a she, I didn't check. Okay, so the bug is now going to rotate faster and faster, because we're starting it from rest and we're applying this force to it. And we're applying the force for 3 minutes. So it also says after 3 minutes, the tire is spinning at a rate of 3,500 degrees per minute. Degrees per minute. What the heck? Degrees. Oh, man. I don't get it. Okay. Well, let's see. I bet you do a little bit, because you know there are 360 degrees in a circle. So this bug has now traveled after 3 minutes. It's actually moving at a rate of 3,500 degrees per minute. So after 3 minutes, the tire is spinning at a rate of 3,500 degrees per minute. Let's take a look at that number. 3,500 degrees per minute. You know what that is? That's velocity. It's a weird way of saying a velocity. I mean, you haven't seen it like that before, but it's a velocity. 3,500 degrees, that's a distance. Remember, degrees is a distance. If we were to go 1 radian along a circle, we have covered a certain amount of degrees. There's an angle there. So that's a distance. And that's minutes of time. So that's distance over time. That's a velocity. The only problem with that velocity is it ain't going to work for us, because we know that we have to have this thing in radians for 2 reasons. One, it says so. The other reason is because it says we have to have an angular we want velocity in this, yeah, an angular distance. Okay, so that means we can't have 3,500 degrees per minute. We have to convert it to radians per second. That's the international system way of talking about things spinning in terms of their velocities. So let's do a conversion. 3,500 degrees per minute. Both units have to be converted. So you pick and stick. Pick one and just ignore the other one. So let's go degrees on the bottom, so it cancels. And we have to go to, what do we want to go to? Radians. We want to go to radians. Degrees are radians. So radians, and okay, now you know, yes you do, you know that there are 360 degrees in a circle. You also know how many radians there are in a circle. Yes you do. 2 pi r. 2 pi r means 2 pi radians. 2 pi radians, 2 pi r. It's the same thing. So 2 pi. There are 2 pi radians in one complete circle. So this is going to cancel out my degrees, leaving with the unit radians, which is what I want. I want radians per second. And the 2 pi is just a number. I mean, we can actually put that in now as 6.28. that works. I use 3.14 for pi, so double it, 2 pi, 6.28. That one's converted. We've got our radians. Now we have to get the meters, or minutes. So here we go, minutes. On the bottom, and we want to go from minutes to seconds, or radians per second. So seconds, you know that 1 minute has 60 seconds in it. So minutes are gone. Radians per second is what I have. Do the math. And I have a final velocity. Because remember, this is the final velocity after 3 minutes of spinning around. So after 3 minutes of spinning around, now think about it, 3,500 degrees per second. If you take that and divide that by 360, you'll get how many revolutions it's making. But we want to know how many revolutions per second. So we're going to have to make sure we get the seconds in. So here we go. Math, 3,500 multiplied by 6.28. Enter, divide. 360. Enter, divide by 60. And hit enter. Ooh. Let's try that again. 61.05, 61.05 divided by 60 equals 1.02. So just barely, okay, 1.02, just barely over 1 radian per second. Radians per second. Now, if we go back to the bug, so we'll remember that number. We're going to write that number down. Get rid of our conversion. Get this out of the way. We've got that converted. Remember that number we just converted into 1.02. 1.02 radians. Rads, man. It's so rad. So rad. So groovy. Come on, we all remember we used to talk like that when we were kids. Groovy. Rad. Yeah. Radians per second. So here's your circle. Here's the bug. No, actually, that's not the bug. That's center of the circle. Here's the bug. So that means the bug in 1 second has traveled just a little bit more than 1 radian or 1 radius length. So that means the bug has traveled in 1 second about that amount. So that's actually not this fast. You think this is being a bicycle wheel and it's been accelerating for 3 minutes. Because it's after 3 minutes that's the speed. It's not accelerating very fast. Somebody might be just barely tapping it, and eventually it gets to a speed of that fast. Well, that's not very fast for a bicycle wheel, but all right, that's what the problem's asking. So let's go ahead and continue. Oh, is that the answer? Are we done? Can we move on? Can we be done? Please let me be done. Let's see. What is the angular distance that the bug travels in 3 minutes? So not the velocity, what's the distance? But this is not a very difficult thing to do. Now the thing is, here's what we have to introduce. We have to talk about the fact that the big three, the original big three, remember that? All right, big three. Let me write those down again. They keep coming back. VI squared plus GAT. Remember those? We're going to need them again. Now, there's a slightly different version when you're talking about things that are going around and spinning as opposed to things going straight and up. Now, we use these things for going straight and up and down. That's what we did, up, down, straight. We actually use them for projectiles as well. We needed to use these again for projectiles. We're going to use them again. But this time, we're going to change the way the symbols look. When you're talking about things rotating, the velocity is no longer a V. It becomes the Greek letter omega. Kind of looks like a W. And the omega velocity, this is rotational velocity as opposed to linear velocity or even centripetal velocity. We're talking about centripetal, we're talking about meters per second. We're talking about radians per second here. So we just change the symbol to show that. So here we're going to have omega I plus A. That gets changed to the Greek letter A, which is alpha. And then time. Time doesn't get changed. It's the only one that doesn't get changed. Time probably feels, well, I tell time, don't feel bad about yourself. You're special. Okay, you are special. Time, so you get to stay the same. Everybody else has got to change their symbols. So all I'm going to do here, and distance is theta, because as we showed earlier, that along a circle that you're traveling a certain amount of degrees, that's a distance. So we get theta for that one. This is equal to omega I times t plus 1/2 alpha t squared. Here we have omega f square root omega I plus 2 fish, call that the fish, times my theta. They're essentially the same equation. The only difference is I just changed the units. And some of you might be saying, well, why would I bother using any of these? Why not just use these? It's the same thing, you just change the units. Correct, that's true. So you can think of any kind of velocity equations using the big three is still the big three, including this rotational stuff. But the reason I point this out is it's going to remind you that you have to use radians. You have to use radians over here. Radians per second squared. Radians per second. Radians in terms of distance. This means you better be using radians. This means you better be using meters per second. So if you can remember that the equations are set up the same way, and we use radians for these, you can go ahead and use these and just think radians, think radians, think radians, because they are the same equation, but think radians. Okay, thinking radians, what do we have? So I'm going to do it the official new equation versions right here. What do we have? This was a final velocity. We calculated we converted. We were given the final velocity, but we were given it in the wrong units. We're given it in degrees per minute. We converted it, the final velocity, to radians per second. So we have that. We also know it started from rest. So we know the initial velocity. 0. Okay, what else do we know? We know the time, because we were told 3 minutes. 3 minutes. 3 minutes. 1 minute, 60 seconds. 60 seconds times 3, 180 seconds. So we know the time is 180 seconds. And all you need to know is 3 things to use any of the big 3 equations. You only need 3 things. We have 1, we have 2, we have 3. We are ready to rock, Squidward. We want to figure out how far, that's our distance, or in using radial distance, it's going to be theta. We want to know how far the bug has gone. How far has the bug traveled in that period of time? Okay, so what equation should I use? I want to solve for distance. Well, that doesn't have it in there. I can't use you. Okay. This one's set up for distance. Come on, come on, come on, come on, come on. The initial velocity is 0. Yes. So we have that. We have the time. I don't have an acceleration. Dang it. Now, here I can also say, well, just try this one. I have the, a final velocity, initial acceleration. So maybe I should not have been so quick as to erase that first equation. Well, yeah, but you can solve for the distance using this. You can solve for theta. It's not in there. Correct, you can't. But you can solve for the acceleration, which you're going to have to do, because in order to solve for distance, you need to know the acceleration. You can't have 2 variables unknown. So we're going to have to solve for the acceleration first, then use it, throw it into this equation. This is easier, because it's set up for distance, and solve for what we really want to get, the distance. So we need to figure out what the acceleration rate is, and we can do that. We have the information to do that. Final velocity is 1.02. Initial velocity is 0. Acceleration we're trying to find. The fish, put a little face on him. You're so cute. Blub, 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 blub. And the time we know is 180 seconds. Okay, so do the math. So it's going to be 1.02. I'm going to subtract 0, so 1.02. divided by 180. Ooh, that's going to be a small number. That's going to be a small acceleration. Well, if you think about it, it should be, because remember I was saying at the end, the bug was only moving like 1 radian. After 3 minutes of accelerating, only 1 radian per second. So that means we didn't accelerate this bug very fast. So 1.02 divided by 180. That comes out to be 0.0056. 0.00. I'm going to call it 0057. We'll round it. 2 significant figures. Okay, so that is radians per second squared. That's my acceleration. That equals the fish. Now we have enough information to finally get to the answer to this problem, which was to solve for how far the bug traveled during that time. And I can go ahead and use the equation that's set up for distance. So let's clean this up. Okay, don't need you anymore. Okay, we'll get rid of all this stuff. And we need you. Okay, I remember the other numbers. So here we go. Distance equals. Now, this is the D is equal to VI, but I'm not going to use V. I'm going to use the official symbols. Well, you don't have to if you don't want to. You can use the other ones. Just remember, it's got to be in radians. Fish times squared. Plug in. Boom. Equals initial, which is 0. So this whole thing just cancels out. Gone. 1/2 fish. 0.0057 times the time was 180 seconds squared. Okay. How far did the bug travel? Bug traveled 180 times 180 equals times 0.5 equals times 0.0057 equals 92.34. What are my units? Very good, Billy. Radians. This is going to be in radians. This was in time was in seconds. This is in radians per second squared. Seconds cancel. Radians. Now you might be saying to yourself, Self, I have no idea how far that is. If I ask you how far is that, you're going to go, I don't know. I don't know. If I told you that the bug went 92 meters, then you have an idea. 92 meters is about the length of a football field. So you go, you get that. If I took 92 feet, you get that. 92 radians, I don't get it. Well, how am I supposed to know how far it goes? Here's how. It's very simple. Let's get this into meters. How do I get that into meters? All you need to do is multiply by the length of the radius. The length of the radius in meters. Now, I don't think this problem gave me the radius of the bike tire, but the bike tire is about yay wide. So let's say that the length of the radius of a bike tire is 1/2 meter. Okay, about 1/2 meter, maybe a little bit less, but we'll call it 1/2 meter. So 0.5 meters. If I multiply, see the radius here is 0.5 meters for that radius. 0.5 meters per radius. All you need to do to get radians into meters is multiply by the length of the radius. It's pretty simple. So this would be about, do the math on that in my head, so about 46. Yeah, 46. So that's about 46 meters. The bug in 3 minutes traveled 46 meters, which in 3 minutes isn't very far. As we said earlier, the bug's not moving very fast. So 46 meters. So however, if the radius of this bicycle tire were 8,000 miles, that's a big bike. Then that means the bug would have traveled a lot farther. So how far in meters we travel depends on how big that radius length is. To get radians into meters, just multiply by the length of the radius in meters. Right. 46 meters. Okay, finally. I know that took a while. Sorry, that's the way it goes.